this is all hopeless. But then once they tell you that they, their goal is this error rate next year, you just say, okay, what can we do with that error rate next year? So you just say, basically what people do is at the first level that they often use sort of a very inefficient code, because inefficient in the sense of maybe it has a higher overhead or something, but it can tolerate a high noise rate. And you use that just to get the effective logical error rate fairly low, and then maybe you can just use one more level of encoding, but with a better code, with a more efficient code, to get the error rate down to 10 minus 11 or whatever, 10 minus 13, or whatever you want. Okay, so overall, this is kind of the picture of where the field was in 2005, I guess. But I mean, this field is really, it's very interesting today because these kinds of pictures are just dreams, really, right? Because we don't have quantum computers that are that big, or we can't hope to. And so really what we want to do is, again, with these NISQ devices, where we only have hundreds or 1,000 qubits or something, how can we do very low overhead, some sort of error reduction or some sort of fault tolerance that's maybe less than general fault tolerance, or some interesting thing to reduce the noise rates. Okay, develop fault tolerance schemes that maximize the noise rate with as low an overhead as possible. Okay, yeah. So a lot of the research has condensed on sort of talking about the surface code, which is a particular code I'll mention. And other groups, so Google, for example, is doing that. Other groups, for example, Microsoft has been looking more at different, larger quantum error correcting codes that I'll talk about. Okay. Okay, that's not that interesting. I think I'm just trying to come up with excuses to cite my own papers. Yeah. So well, here's one theme. So one theme of some research is to try to use more efficient codes. So here, I said there exists a 5-qubit code that takes one logical qubit to 5 physical qubits. More frequently, people use a 7-qubit code just because it has nicer properties. All that I'll explain. But in fact, in more recent research, people are trying to use more efficient codes. So for example, you can code 7 logical qubits in 15. So this is bigger, which is bad, but the ratio is better. It's like 2 to 1 instead of 7 to 1. So you need fewer physical qubits. The downside of using a code that encodes multiple logical qubits, like 7 or even many more than 7, is that it becomes trickier and trickier to actually do things. So like this is very good for quantum memory. If the logical qubits, if you just want to keep them stored forever, this is very good. But if you want to do interesting operations on them, it's easy to imagine that it's harder to do an operation in this kind of code than in this kind of code, because you have 7 things mixed up in some weird way.
Yeah, I was about to ask you about transversality.
Yeah. So things get harder.
So that's in this paper by Carrington, right? Sorry.
I mean, there's lots of papers. You shouldn't really cite that one, but yeah. More efficient. Oh, I see. So I'm just talking about sort of problems that people have been studying. And another really efficient one is a really important question is okay. So yeah, you want to use the code, and often these codes are stabilizer codes, so they only use so the code space is the simultaneous +1 eigenspace of a bunch of commuting Pauli operators. And so Gottesman, Knell, all Clifford gates, all that stuff makes sense. It all applies. But getting a universal set of encoded gates is often harder than just getting a set of encoded Clifford gates. And so another problem has just been how to augment the Clifford gates to get universality as easy as possible. And this is a whole field. So the field is often called magic state distillation. And people try to come up with reducing the overhead as much as possible. So this is some overhead according to the target error rates, and they're trying to get the curve as low as possible with different methods. And this is important because actually a lot of the overhead, as I said, in like Shor's algorithm or any algorithm, most of the operations are not C0 gates.
Yeah.
Most of the operations are like these weird rotations, so these universal operations or Toffoli gates or something like that. And so it's really important to get the non-Clifford operations as efficient as possible. Okay, so then this is just, I mentioned this last time, which is maybe this whole, maybe fault tolerance isn't necessary at all because somebody's going to develop a magic quantum transistor, which is not magic, but one of these topological quantum systems or anionic systems, or a self-correcting quantum error correcting code in a physical device somehow. I'll explain what that means. Okay, so solutions needed. Right, so this is from Rigetti just before he started his company, I think. This technology is a strong candidate for the immediate construction. Yeah, so then he started a company. They still don't really have it, but now it's 2012. But yeah, you do see these plots which are somewhat nice, where they show this is for superconducting qubits. They show this is I don't know. Oh, the T2 time. So the T2 time is the dephasing time. You know, the amount of time before you have Z errors that destroy the information. And yeah, so back when it was NEC doing the first superconducting qubits, they had only nanosecond time, which is very poor. And then it got better and better. And so now, I guess the typical 2-qubit gate time is what? 10 nanoseconds, 12 nanoseconds, let's see, 10, they're saying 13 nanoseconds. So it's on that order, tens of nanoseconds for these superconducting devices. And the lifetimes as of 2011 were on the order of 10, 100, all right, that's microsecond, 10, all right, so that's 10 microseconds. I think now then, what are they on? They're on hundreds of, I think they're another order of magnitude above, so they're on the order of hundreds of microseconds, I think, for these superconducting devices. So that means if your typical gate time is tens of nanoseconds, and we're up to hundreds of, so 1, 2, 3, we're between 2 and 3 orders of magnitude, so the error per gate is going to be roughly between 10 minus 3 and 10 minus 2 for current technologies.
What does that mean, reproducible?
So I think that means like somebody, so above the curve, somebody reported it, but nobody else was able to do the same thing. Yeah.
Okay.
Somebody
That's very scientific.
Yeah, I don't know. Yeah, I mean, it could be that you don't believe this person, or I don't know. Yeah. But yeah, I mean, overall, we do believe this, and lots of people who know this do believe this. All right, and so this number here, this is 1, 2. This is a little bit more than 2 orders of magnitude above the 2-qubit gate time. So that's like the threshold, because that's like saying we do about 100 or a little more than 100 2-qubit gates before the qubits are decohered, are lost. And so therefore the error rate per gate is roughly a little bit less than 1%. And that's like what Yannick Knillen had as his rough threshold. And so once you get below this threshold, or once your qubit lifetimes get above this number, above this threshold, then you can hopefully start to do interesting things. Of course, it's more interesting the farther below the threshold you are, because as we saw, when you're really close to the threshold, the overhead is really, really high. Okay, so that's the end of this. So